Thanks everyone for coming. I'll talk a little bit about algorithms for solving constraint satisfaction problems and some applications to codes. I should say this is based on joint works with 4 great students, Vedat at University of Waterloo, Fernando and Dylan at University of Chicago, and Shashank Srivastav at TTIC. Some of them are in the job market, so look them up. Okay, so I'll kind of go in the reverse order of my title. So I'll talk about applications to codes, or I'll get motivated by some questions related to codes, and then slowly we'll make our way to constraint satisfaction problems and algorithms for solving them, and so on. And please stop me if something doesn't make sense. I'm not an expert on coding theory, so please do correct me if I'm missing some references or if I'm saying something which seems egregious. So yeah, okay. So let me motivate this by trying to construct codes or an operation which is used to amplify distance for codes. So let's say we have some code which is, for the purposes of this talk, nothing but a subset of f2 to the n. So each element is an n-bit string. And let's say the distance of the code, which is the minimum distance between any 2 elements of the set, which I'll denote delta C0, is at most 1 plus beta 0 divided by 2. So again, for the purposes of this talk, we will not worry too much about this code. We will not worry too much about beta 0. So you can just think of beta 0 as some numbers somewhat smaller than 1, but not an arbitrarily small constant, just some fixed number. Okay. And what we want to do is try to come up with a better code where the distance is actually as close to half as possible. For a binary code, that's the best we can hope for. So what we'll try to So I'll represent what we want to do in a couple of ways. But here's one way of trying to improve the distance of this code. We will write down the bits of a code word as just on, let's say, n vertices of a bipartite graph with n vertices here, let's say m vertices here, and let's call them y1. And let's say the right degree of this graph is k, which means that each y is connected to some tuple of neighbors, let's say I1 to ik, and so I will define yi to be the parity. This is all mod 2. Another way of saying this is I could have written down the incidence matrix of this bipartite graph. Let's say and now I want to kind of construct bipartite graphs or incidence matrices such that the new code, which is kind of created from the old code by doing this operation, has much better distance, and at the same time has some other nice properties that we can maybe decode this code fast, etc., etc. Okay. Is the construction okay? Just the definition. I'll think of this W in a couple of ways. So I'll overlap notation a little bit. I'll think of it as a matrix, but I'll also think of W as a collection of tuples of size k. So you can think of it as an ordered hypergraph. So I'll just think of this as an ordered edge or a tuple, and I'll use E for that notation. Okay. So I'll just overload the notation a little bit. I'll think of it simultaneously as the incidence matrix and an ordered hypergraph. Okay. Questions? Okay. And of course, okay. And there are a couple of questions we want to think about. So, okay, just going back, let me define another parameter, which is the bias of the code. So it will be slightly cleaner to work with that. Just the fact that the distance of the code is of this form. Let's say C0 is a subspace even. So I can use this to say that if I look at the number of zeros minus the number of ones, or the fraction of zeros minus the fraction of ones, then the difference is at most beta 0, and I'll kind of work with this parameter instead of the distance explicitly. I'll just call this the bias of the code.
So maybe on the left-hand side you meant every code word has weight between 1 minus beta naught over 2 and 1 plus beta naught over 2. That's what you thought.
Yeah. So okay, let's say so then I can talk of distance of the code and weight of the code as the same thing. So let's just work with subspaces.
This is also called the beta zero bias.
It's a beta 0 biased set or beta 0 biased code, right? And we want to construct from some fixed beta 0 biased subspace. We want to construct beta biased subspaces maybe for arbitrarily small beta, and then we're trying to use this operation as a way to do that. Okay. So so the goals I'll be interested in is constructions of maybe minimize the kind of redundancy this operation introduces, which I'll use as a proxy for the rate of the code, although the rate really also depends on what is the rate of the original code C0 or what is the amount of redundancy in that code. I'll ignore this for the purposes of the talk. I'll just think of this as some good code with some constant parameters that we can start with. So I'll only focus on this ratio m over n. And the question which is perhaps the more important one for this talk is let's call this new code let's call this new code C. So we are starting from this code C0, constructing a code C. We want to basically work with matrices W or hypergraphs W, which allow us to reduce the question of decoding the code C to the one for C0. Okay. And we'll focus on this part a little more later. All right. So let me say a little bit about just the first 2 points, which is finding good W's which reduce the bias. And let's say I look at a matrix W which has this property that if I look at the bias of a single code word or a single element Z, okay, where the bias of Z is just this quantity, and the bias of the code is just the maximum of this overall Z. Let's call such So we'll call W a good matrix or an amplifying matrix if this is true not just for Z's in the code C0, but just all of them, which means that if you have any code word which, or any string which has some balance between the number of zeros and ones, then the resulting vector also has a much, the number of zeros and ones is much closer to half each. Okay. And let's just take a couple of sanity check examples. So okay, let's just first see what happens for this one as just as an exercise. So now we are allowed all choices of I1 to Ik independently, and the value of the corresponding bit will be just so if we just take the complete collection of all k tuples, the bias just powers. And so if this was beta 0, then this will be beta 0 to the k. And so there is, of course, a nice explicit W which will reduce the bias, but the rate is terrible. Okay. Now,
so in the picture, it corresponds to having y1 to yn to the k.
yes, y1 to yn to the k. So it will be a very unbalanced bipartite graph. And yeah, so, okay. This is true also if you pick W at random. And to get concentration in this argument, roughly a size of 1 over beta square times n would be enough if you want this to be beta for all starting z's. So a random set of this size would also work. Right. So this is the best you can hope for because of Gilbert-Verschamov, and which says what is the rate of a code at a given distance. And here we are talking of rates at of codes at distance, which is half minus epsilon or half minus beta, or maybe half minus beta over 2. Okay, so that's the random construction. Let me say a little about some constructions which get close to this, but again, this is probably a very incomplete history. So, so I don't really know the year for this reference. Tashma kind of credits it to, or sort of cites a 2012 lecture notes of Andrei Bogdanov. I'm not sure what the year is, what correct year I should, roughly. Where give a construction which is size n over beta to the 4, and the collection, and W is obtained by looking at walks of length k minus 1 on an expander on the set of bits of Z.
And this has the property of beta, some 0.1 beta, is that correct?
Yeah, it's 0.1 beta amplifying. So yeah, actually all these constructions I'm stating are not just amplifying for elements of the code, but they are beta 0 beta amplifying for some constant beta 0, and we can take it to be 0.1. Thanks. Okay. And
maybe it's very natural to try to de-randomize this construction of basically n to the k is just independent sampling of k tuples by walk on an expander graph.
right.
Only that you don't want a hitting set, a good hitting set, you want a Arity. Right?
Yeah, so you want something which kind of samples this, or and so in some sense we'll see this a bit of a trade-off, that we want something which is pseudo-random or looks like this random structure, although in terms of decoding, so random is bad, or if I actually look at the kind of constructions which just random sampling would give, one doesn't expect a good algorithm for decoding the relevant code C. So we want something which is kind of pseudo-random enough to capture this part of the argument, but at the same time has some properties which are different from just and then. So I'll basically write two properties. One is this amplifying, the other is something I'll call splittable, and we'll try to construct instances which have both properties. And turns out this construction actually has both properties, and then I'll also mention more. The celebrated result of Tashma, which gives near optimal construction. So the exponent is very, very close to 2 and goes to 0. The exponent goes to 2 as beta goes to 0. And here you don't necessarily look at all walks of length k minus 1 on an expanding graph, but you look at walks coming from a very special, first of all, the graph is not an arbitrary expander. It's an S-wide replacement product of two expanders, and you look at the walks coming from this corresponding collection. Okay, so I don't necessarily need the details of this. I just wanted to say a little bit about what is known in terms of the size of W. Let me say a little bit about decoding. And here, yeah, so there's not that many results I know. So please let me know if there's something I missed. Also, I should say that this is by no means the only kind of set of works which try to amplify distance or reduce bias by this kind of XORing copies, which is direct sum. There's lots of works on the randomized XOR lemma, etc. So I'm not citing a lot of other works. These are just more directly relevant ones. Okay. In terms of decoding, the works I know are for direct product. Where the code is slightly different. So instead of YE being the parity of these bits, you actually write down all the bits. So it's over a larger alphabet. And here, because the alphabet is large, you want the distance of the code to be maybe more than 1 minus beta rather than close to half. And the work of Allen, Brook, Naur, and Roth gives unique decoding for this code. Again, it reduces the unique decoding question to the decoding for C0. So all of this is assuming C0 has good algorithms. When but the alphabet is large, so it's not exactly comparable to the sampling result there. And the work of Irit, Prahlad, Tali, Inbal, and Amnon, which kind of most directly inspired our work, which gives list decoding. When W is doubly exponential in beta. In the list decoding setting, if you can do list decoding for the kind of codes which come from this parity operation or direct sum, you can do list. You can also do list decoding in the direct product regime, and then there is a standard reduction. So the direct sum result would be slightly stronger. Here, this was done for direct product by reducing it to some sort of constraint satisfaction problem. And I'll show sort of a slightly more general framework which works for direct sum, but also gets somewhat better parameters. Are there any other results on direct sum that you know of that I'm like, these are the only ones I could find? No. So they're both constructing some special W. ABNNR in particular shows that if this graph is a good sampler, then you have a unique decoding algorithm for the new code if you have a unique decoding algorithm for the old code. And here, you need a structure which is called a double sampler, which comes from high dimensional expanders. Both of these give some explicit W, or well, some family of Ws under which you can do this. Not for all. Okay. Any other questions? Okay. So let me So let me at least briefly say what the result I'll talk about is. So this. So there exists W, which is quasi-polynomial, and you get bias amplification to of the construction is not novel, it's just expander walks, so it's just using the Rosenman and Wigderson construction. What is new is you can get, and you initialize it with slightly different parameters, and you can get unique and less decoding algorithms for the direct sum. And then it also implies for and then there's some recent results or sort of recent follow-ups where maybe you can try to get this quasi-polynomial down to polynomial, or even try Rashomon construction, but I'll speculate on that later. So what I want to kind of mention is the general framework, which uses what is called the sum of squares STP hierarchy. To solve some sort of constraint satisfaction version of this problem, and then the framework is kind of nice enough to incorporate list decoding in a rather natural way. So I just want to show that framework and then say how we can tune the parameters. Okay. And also mention a general condition under which this framework can be instantiated, which I'll get to as we proceed. Okay. Yes.
But it's not known to be.
No, double samplers, at least for the definition required here, they do exist, and they can be.
Explicit.
Sorry? So, from what I understand, the constructions of high-dimensional expanders from Ramanujan complexes are double samplers. And so, these are explicit constructions. They're not explicit enough that I understand them, but they're explicit.
In your thing, everything is explicit?
Yes, so here the construction is just walks on expanders, so they are even explicit enough that I can understand them.
Okay. So you're not using double samplers?
No double samplers. Okay. Yeah, so I'll use a weaker property which I'll call kind of splittability of W, and I'll show that expander walks satisfy that already. So we don't need double samplers for this result.
But double samplers also satisfy?
Sorry? Yes, double samplers satisfy. Well, okay. I'm not. So the constructions of double samplers satisfy this. Maybe when we come to it, I have to think about if I can just state it as a property of just in terms of double samplers. Do swap walks mix for double samplers in general?
I mean, when you move from definition of sampler to definition of expander, you might lose something that makes no sense.
I see. Okay, so we'll come to it, but if you only lose factors depending on k, I think we might be okay, at least with these kind of parameters. If we really want to get to Tashma's constructions, then we will have to worry about things. Okay. So let me first sort of just talk about the corresponding code and the unique decoding problem. Let's not worry about list decoding. And there's a smarter way of doing unique decoding. This is like the dumber way when I do it, and then the smarter way when my students do it. So we'll get to that later. Okay. So let's first do unique decoding. Okay. So let's recall again what we had. We had, let's say, some z1 to zn, which was in C0. We kind of created these y1 to ym, and we transmitted this now. Okay, and we got some corrupted values, which let's call y1 tilde to ym tilde, and y was wz. We don't know z, of course. So what we are trying to find is the closest z in C0, which minimizes the distance to what the code transformation would do and what we received. And that's also so the distance of yz from y tilde is just 1 minus the fraction of XOR conditions that we can satisfy, where the right hand side is given by y tilde. And okay, and this kind of problems are just constraint satisfaction problems. So what I'll do is I'll forget about this condition that z is in C0, and then just search over all z, which is just a vanilla kind of constraint satisfaction problem. And then I'll say that because of amplifying property of w, it's enough to find any z, and then we will be able to turn it into something in C0 by the unique decoding algorithm. Okay. So we will try to solve a constraint satisfaction problem or we'll think of this w as an instance of a constraint satisfaction problem where each tuple corresponds to a constraint. So let's say a little bit about which are the kind of problems we will be able to solve. So let's say the actual definition is a little more involved. Let's say for the purposes of this talk, k is the power of 2. And we can write each edge in w, or we'll just split each edge in w in two parts, E1 and E2, where and let's call W1 the collection of E1s which appear in the above decomposition, and W2 is the collection of E2s that appear as the second half of some tuple. Okay. And we'll say that W is gamma splittable if I look at the following matrix where rows are indexed by W1, columns are indexed by W2, and you have an entry E1, E2 present if the union is present in W. Again, let's assume that all the rows of this matrix have equal number of non-zero entries. Otherwise, we'll need to look at some measures on the rows and column sets. We can ignore that for the purposes of this definition for now.
This is a very sparse matrix.
It's a very sparse matrix. Sorry? It will be a very sparse matrix, yes. And we'll write this matrix explicitly for expander walks in a minute. So we'll say that W is splittable if this matrix so the second singular value of this matrix when all the values are normalized to be between 0 and 1 singular values is at most gamma. And so this is a recursive definition. We will want the collection of tuples W1 and W2 to also be splittable unless they only consist of singletons, in which case we'll kind of terminate there. Okay. So that's the definition of splittable. And I'll say that in general, when you have a system W which is splittable, you can solve the corresponding constraint satisfaction problem. In particular, expander walks correspond to a system like that, etc. So we'll use this definition to give our algorithm.
So in an expander walk, if you just split the walk of length to the K recursively, then each one of these matrices will be basically like the adjacency matrix.
Precisely. So yeah. So in expander walk, and I'll kind of write this down in a minute, but it'll just be the tensor of an all ones matrix, a tiny all ones matrix with the adjacency matrix of the graph. And because the tensor structure, the second singular value will be whatever is the second eigenvalue or the second singular value of the graph. So if you have a good expander, walks on that will give you a splittable collection. Okay. So a random collection of k tuples will be not splittable. In fact, it will be very much like a matching, like this kind of graph. So if you take a random collection of 4 tuples, no 2 4 tuples will intersect in more than one, with high probability, with more than one sort of element. So, sorry?
A random sparse collection of 4.
Sorry? A random sparse collection, yeah, if it's not dense. But not dense as in, I guess if you look at 4 tuples, you can go all the way up to n square, and it would still not be dense enough to, and then the graph would still be pretty much like, or like this matrix would still have one entry in each row. Right. So the general result for constraint satisfaction problems, which follows from an earlier work with Vedat and Fernando 2019, is that if you have a system W, which is let's say epsilon over k splittable, Then where opt is the best you can do over all z. Okay. So if you have a constraint satisfaction problem, I mean, more generally, it doesn't have to be of this particular form, really. Each constraint is on k variables, and the instance is epsilon over k, poly epsilon over k, I think square should be enough, splittable. Then you can find an almost optimal solution. And this will be enough for our unique decoding algorithm. Okay. So, okay. Any questions about the statement?
We should think of k as constant.
So, not really for the amplifying kind of results, because if we start with a constant beta 0, then k would be really log 1 over beta, and which is kind of why we get quasi-polynomial here. If you want to kind of get better than this, then there are sort of so yeah, for the coding application, k is not constant. In fact, the dependence on k matters. So what I'm stating are not necessarily the most optimal form of the results. There are kind of more careful ways of arguing which can yield better dependence. And also, there is ways of applying this result where k is not log 1 over beta, but something intermediate. So yeah, but at least for this, k is not constant. It's log 1 over beta.
Does it come from the constant in the splittable, or where does it come from?
It comes from the constant in the splittability. So the rate is, if the degree of the graph is d and the length of the walk is k, then this is d to the k. Because for at least the naive algorithm, the accuracy I will require will also be of order beta, or polynomial in beta. So the degree of the graph will also be a polynomial in 1 over beta. So this will be polynomial in 1 over beta to the power of log 1 over beta, which gives this. Okay. And in fact, that's kind of the bottleneck for this result, that the eigenvalue of the graph needs to kind of depend on the accuracy parameter, which is what limits the rate here. Okay, thanks. More questions? All right, so so let me first say, or is everyone okay with the fact that walks on graph give a splittable collection, or do you want me to show the proof? Maybe let me just show it for walks of length 3. So think of and let's split it into, and now W1 and W2 will be just edges in the graph. The first 2 elements in a walk of length 3 are just going to be some edge in the graph. ordered. So, and these are connected if and only if I2, I3 is an edge in the graph. So this will just consist of D cross D blocks, one for each element of the adjacency matrix of the graph. So the matrix will be just the adjacency matrix of the graph tensored the all ones matrix. Okay. All right. So that at least shows that nice splittable collections exist. And now let me quickly say why, if we have this algorithm, we can do unique decoding, and then we can take a break before we go to the SOS part, which actually goes into the algorithm. Okay, so again, going to this picture, we started with Z, we got Y, and we got W tilde. Now, suppose the corruption was at most eta, which is the amount of corruption or less than equal to the unique decoding radius so of the code, then our algorithm will find Z tilde which has error at most epsilon more. So it satisfies epsilon fraction of constraints less, so the distance is at most epsilon more. And by triangle inequality, the distance between Z and Z tilde is not too large. Okay? And I'll instantiate those parameters in a second. If this implied that the distance between Z and Z tilde was not too large, less than the unique decoding radius of C0, then we'd be done, because given Z tilde, we can just do unique decoding for it and find some element of C0. Okay? And this is precisely what the amplifying property is, or rather the contrapositive of the amplifying property. It says that if these two were at a large distance, then these two would also be at a large distance. Okay? And concretely, let's say eta is less than half of 1 minus beta over 2, and epsilon is beta over 4, and Z is or W is beta 0 to half minus beta over 4 amplifying. So we need slightly better amplification than we would just need for the to prove the distance of the code, but at least here it is just a constant factor in beta and doesn't really affect the rates as much. For list decoding, it will affect more. Okay. So if W is amplifying in this sense for all Z and Z tilde, then we will have this implication that Z and Z tilde should be close, and we can just find Z using unique decoding. Any questions? All right, so maybe we can take a short break, and then in the next part I can tell you about the sum of squares hierarchy and how to design this algorithm, and also how to sort of change it to list decoding, etc. Let me briefly say what the sum of squares hierarchy is, or what kind of objects we deal with, and then roughly how the argument proceeds. And I'll actually sort of state it as an object which I called T-local ensembles. There is an additional PSTness property, but it will be kind of hidden in the argument we talk about. Okay, so our goal is to find Z1 to Zn satisfying some property. Okay, so let's say we have a collection of constraints that where each E is let's say a k tuple. Z restricted to E just means the bits of Z in that k tuple, and we check some condition which is denoted by G sub E, which let's say is either evaluates to 0 or 1. It could be that indicator, it could be something more general. Okay, and the goal is to try and find integer values or values in f2 to the n satisfying these conditions. What SOS gives you is distributions over assignments which satisfy many of these conditions, except that they are not real distributions. Okay. So if these conditions are on sets of size k, think of T as something larger than k, so that okay, and these distributions are consistent on intersections. Okay. So instead of a distribution, let's think of a random variable capital Z sub s, okay, which takes values in and let's use this curly brace to denote the distribution of the random variable. So that's what I'll think of as an SDP solution. It's a collection of distributions, okay, all over all subsets of size, and it will have the property that if I look at locally what's happening, so if I just look at whether the condition is satisfied in expectation over the distribution for the relevant variables, okay, then this will happen with a good probability, or in expectation a lot of conditions will be satisfied. I have to be careful about this expectation, so because as I said, these are not real distributions. So when I'm looking at the expectation of Z sub E, I'm going to take the distribution as sort of expectation over the corresponding distribution. Okay, just for, so if this is some 5 variables, I'll only look at the distribution over those 5 variables and take an expectation. Okay. So if I just looked at the assignments that I give in the distribution to these 5 variables, they satisfy the relevant constraint a fair number of times, at least for most constraints. That's what an SDP solution will look like. And
it's possible to say that there is solution, like an assignment which has this property. Yeah, it's a good distribution.
Great, thank you. So an assignment which actually satisfies will be some labeling of Z1 to Zn by 0 or 1, and you can also think of it as as a distribution which has support of size 1. Okay? And you can also think of it as a collection of local distributions, of course. Each of them will have support of size 1, and they'll all be consistent. Okay? And in fact, instead of an assignment, if you had a global distribution, a distribution over all n variables, which had this property, then that would also give you a good assignment, just because this would be an inequality which is true in expectation over a distribution, so at least one of the elements in the support would be good. Okay? So it's good enough to find a true distribution, starting with these kind of fake distributions or these sort of local ensembles. Okay? And they satisfy some additional PSDNS properties, which I'm not going to talk about right now. Okay? All right, so we are given this collection of fake distributions, which are kind of consistent, and our goal is to find real distributions. Right. So, yeah, I mean, in fact, this is what I'll think of as the SDP solution. So, yeah, I'm not even going to talk of any other object. So we solve the SDP. We are given this. Right. Thank you. So, there is a caveat which kind of follows. So if after Ryan showed that you can't just always do this, but for constraint satisfaction problems, this is true, that you can solve, in fact, you can get these fake distributions for sets of size t in time n to the order t. In solving whatever the t levels of SOS might require more time, but I don't need to worry about this for CSPs. I'm sorry? PSDNS has to play a role. Yeah, otherwise, you're right that this is also the description of an LP solution given by the Shirali-Adams hierarchy. But the way in which PSDNS will play a role will be a lemma of Barak Raghvendra Stoyer, so I'll not actually show you the role of PSDNS, or I'll kind of hide it. But yeah, it's important that you have PSDNS. Sorry? So it's not quite SDP plus LP. I think BRS give this sort of faster running time, but it's not obtained directly through SDP plus LP. They kind of sketch an argument which is sort of similar to Guruswamy-Sinop, that you sort of solve the portion of the SDP that you needed and that you need. So it's not quite the same as just SDP plus LP, but they have a faster running time. Yeah, so I mean, this is sort of sketched in the BRS paper, and then Guruswamy-Sinop give a much more detailed proof and more general proof. Okay, so let me just first say what would happen if we were just looking at k equals 2, which means that each constraint is just on 2 variables. Okay. Now, here, I claim that a dream case would be the following, that yes.
Yeah, so
Yeah.
just want to maximize the number of
It's sure. So, right. So let me kind of parse this line and then say what it means. So this is, as I said, the distribution of the two variables I1 and I2, okay, given in this local ensemble. Okay. This is just the distribution of I1 according to this local ensemble. This is just the distribution of I2, and this is just a notation if I think of the product distribution. Okay. And what this is saying is that on average, the joint distribution is very close to the product distribution on a typical constraint. Okay. Now, what does that buy me? So the joint distribution satisfies a lot of equations or satisfies a lot of constraints. Right? So on average, the product distribution will also satisfy a lot of constraints. Okay? But there is a global distribution which is consistent with this product distribution on every edge, which is which will satisfy whatever number of constraints the STP satisfies minus an epsilon fraction. Okay. So if I indeed have this condition that the joint distribution is close to a product distribution on typical constraints, okay, then there is a very simple global distribution. Yeah?
In the case that there is a single assignment that the distribution comes from, single assignment epsilon is 0.
Right, great. So yeah, when you have a single assignment, this is fixed. And in fact, at least if you think of linear equations on two variables, it has to be close to that kind of case because in a linear equation, if you fix the value of I1, it determines the value of I2. Right? So you can't really have too much freedom in both I1 and I2 in the product distribution and still have this kind of condition. Right? So what will happen is that most of them are actually fixed to some values, or these are actually close to some single assignment. And this is finding it. Although this is not true for general CSPs. Okay? So, but yeah, so for linear equations, this is indeed actually close to a single assignment, or at least in each constraint, it should look close to a single assignment. Okay? And what they show is that this indeed happens if maybe you don't look at this random variable z, but a slight modification of it, which is a conditioning of the random variable. So, here W, which will just be kind of a graph. Okay, here I just need epsilon. So it may not be true for the collection of local distributions that you get from your STP, but you can define a slight modification, which is should be just thought of as conditioning, but again, local conditioning. So if you want to look at what is the conditioned local distribution on a set T, you think of what happens to S union T conditioned on some event for the set S, which here will be some particular assignment to the variables in set S.
Are you choosing S at random and alpha S at random?
So alpha S will be actually chosen where according to the distribution Z sub S. So I have a distribution on the set S, and I will use that sorry? It's also random. I mean, it's not uniform. That's, yeah.
So the point is you are trying to use the local consistency.
Sorry? Yeah. I'm trying to use the local consistency to even define this conditioning. And the fact that after conditioning we get into the dream case requires PSTness. So it's not purely an LP phenomenon. Okay. But
Yeah, but what is the graph W? Is it a bipartite graph of the constraints or
no, so W I'm thinking of as just, I mean, in their case it's an undirected graph. In the k equals 2 case. I mean, really it would be directed as I defined it, but you can kind of forget the direction on all edges and then apply this result, and that's the setting where the results works.
what is the graph?
Sorry?
What is the graph?
Oh, the graph. So we have an edge between I and j if there exists a constraint between zi and zj. Variables. Okay. So yeah, in case of linear equations, you can also think of it as a constraint between j and I, so it will be undirected. In general, it can be directed.
So it's a random walk on this graph of length 1.
It's a random walk on this graph of length 1. So it's yeah, it's an expander, and yeah.
Let's say you have a fixed graph,
Mhm.
and I give you a string of vertices which comes from a random walk.
Mm-hmm.
I want to encode the fact that this comes from a random walk as a CSP. So what is it a true CSP?
No, so that is a CSP first of all on a different kind of domain, because here the constraint is not. So in this setting, each edge can encode an arbitrary constraint, or we are just saying the edge corresponds to where a constraint is there. In your case, what you are saying is what you are given is a sequence of vertices, and you are thinking of assigning. So this is in some sense a formal tuple which can take values in terms of, for the first vertex I can assign it to some number between 1 and n, for the second between 1 and n, and then I want to say that this tuple is consistent with some random walk in the graph.
Yeah.
Right. So it can be encoded as a CSP, but it's a bit different from the setup here. But that's a constraint on a single k-tuple. And then you have to tell me what k-tuples do you want to sort of enforce this constraint on, saying that each of these k-tuples must come from some random walk in the graph. So that part will really kind of determine the structure of the instance here. It's not the instance of the underlying graph, but what are the k-tuples you choose to give me for which you want to enforce this.
Because eventually the goal would be to come up with a uniform distribution on all the vertices. At least, so this dream thing which you have written down,
Mm-hmm.
like the way I would understand it is that you are choosing a joint distribution on this Z I1 I2,
Mm-hmm.
and it sort of mimics as though it is chosen in a product.
Okay, yeah. So, yeah, I think this is something maybe Arity also remarked, that this looks a little bit like the expander mixing lemma, the statement that, and maybe if you want to think of the set of values where z is 0 and the set of values where z is 1 as and like either you sample kind of independently from these sets or you sample a random edge in the graph. These distributions, but I mean we can talk a little we can talk offline. This is not exactly the same statement, although maybe there is a relation. So we can. Okay. Yeah, sure.
So even if the constraint had only two variables, k is 2,
Mm-hmm.
if you want to reach precision epsilon,
Mm-hmm.
this theorem is saying to you, you need to take sets of size polynomial in epsilon,
Yeah.
condition on everything in a random set, and leave maybe 2 or 3 free, and then you,
Right.
on average, you get a good solution.
Yes. Okay. So now let's do a very simple kind of extension of this to sets of size 4. So now let's think of linear equations on maybe 4 variables. Okay. And again, maybe the dream is yeah, so I'll just use the triangle inequality, which is saying that this expression is less than equal to another term with 3 and 4. So I'll just split this term into these pieces. And now, so this is where I'll deviate from linear equations a little bit, but I can think of applying the Barak-Raghvendra-Steuer argument to this collection, where now each constraint is on these two tuples. So it's an I1, I2, and I3, I4, and they're connected if they together participate in some 4 tuples. So this is what I was calling W1, W2, and W. Because this is splittable, this kind of graph that I can think of, which has these 2 tuples as vertices and connected if they participate in 4, is an expander. So that's the splittability condition, which tells me that in some sense, this 2 CSP instance can be thought of as an expanding graph. This, because W1 itself is splittable, or the kind of, this is the recursiveness of the definition. So here I will get an expanding graph. So each of these terms will be on an expanding graph. And then Barak-Raghvendra-Steuer tells me that if I still define these kind of conditioned random variables, where I choose a subset at random and condition, then each of these terms will, let's say, go down to at most epsilon over 3. So the whole thing will be at most epsilon. Okay. To be a bit little sort of careful in the sense that the kind of random choice and conditioning for this part should also reduce this and so on. So it's a little bit, but it's not much. It's sort of
Distance is not monotone at the condition.
sorry.
This distance is not monotone at the
No, but yeah, I mean, you can work with some proxies and make this argument work. So essentially, that's the argument. You apply the same. If you do this naively, sort of this is a CSP with alphabet size 4 instead of 2 now. So and in general, you can have, if you split a k tuple, you will get size 2 to the k. And their result actually has a dependence on the alphabet size. So this will have an exponential dependence on k. When you are working with linear equations, you can more or less sort of not worry about the values of both the bits I1 and I2, but just carry some, in some sense, the parity of those, and you can get a polynomial dependence on k. But that's roughly the piece of the argument. And as we were saying earlier, the reason when you apply this, you need the error epsilon to be order beta, which means that the second eigenvalue of these graphs is order beta, which means that the degree is polynomial in 1 over beta, and that limits the rate. Now let me say maybe a little bit about how you can extend this to list decoding, or what the framework is. I probably won't give the analysis. But is the flavor of the algorithm okay? Okay. Sorry?
This is for decoding the direct product, not the direct sum.
I mean, this also works for direct sum up to this exponential dependence on k. Like if you are willing to, because this is true for any CSP that because if all these terms go down, you will find a satisfying assignment to the CSP. And our CSP was direct sum, so it will find a satisfying assignment to the direct sum CSP. Okay. So in fact, it works more generally where you can do kind of a lifting using any operation, any local operation, and it will work for all of them. All right. So maybe I'll keep this. I'll do the list decoding part here. Sorry? Dependence on, so in general, each of these terms will need to be something like epsilon over k. Or, yeah, so basically you'll get a binary tree with like k leaves. Here, the conditioning set size was polynomial in whatever you wanted these terms to be. So here it will be k over epsilon, polynomial in k over epsilon. Up to the fact that there is also an exponential dependence on k coming from the alphabet size, but we can get rid of that for XOR. Okay, so the.
Are you saving anything by doing this binary tree as opposed to isolating a variable each time?
Not really. I mean, I mean, at least as stated, it doesn't really save anything. Sort of, we could have split. Yeah, I mean, I didn't mean like a balanced binary tree. I just meant any binary tree. And we kind of state the condition of splittability as saying that there exists a binary tree such that each leaf corresponds to a graph with a small threshold rank. It doesn't really have to be a balanced binary tree. It's just kind of to illustrate. Otherwise, the terms, kinds of terms here. But that's so yeah, so you have to have k leaves, so it doesn't, at least in this naive style of the argument, it doesn't help. Maybe there is some way to use it, but I don't know. Okay, so, sorry. Oh, you mean for the walk construction, or?
Yeah, for the walk construction. I mean, if you take any
Yeah, yeah. No, yeah, I mean, in fact, Tashma's construction, a slight modification of it is also splittable, so you can use that. It's just that, at least naively, as I stated, because we still need a strong dependence on the second eigenvalue on the error parameter, even if we try to instantiate an S-wide replacement product, we will not get better rates.
Yeah, I don't see it, but somehow this is in this work with Jan Rosenman. You didn't get the optimal thing.
That's true.
That protection. I'm not saying this.
Yeah.
Who knows?
Yeah. Yeah. I mean, yeah. So, telling it, I mean, there is a slightly better way to analyze that construction. It's work in progress, but yeah, sort of this is you can do better than the algorithm I just stated for that construction for sure.
But it remains polynomial.
No, I think we can get polynomial.
Okay, yeah, that was my question. Yeah, you can get polynomial.
So, the thing, I mean, sort of, it's a little circular. So we do unique decoding, but using our list decoding algorithm. So the problem with this whole construction is that the error in the unique decoding algorithm, as I stated, needs to be comparable to beta, which requires a very strong condition on the eigenvalue, which then puts a condition on degree and so on. So we actually run our list decoding algorithm, but with constant error, and use that to do unique decoding. And then the error sort of does not need to be as small as beta. And with few other, so then you can kind of actually go to polynomial rates instead of this quasi-polynomial bound. Okay, so just to say roughly what we want to do with list decoding. So here what we said was that you kind of conditioned on a set S and an assignment to the set S, and that gave you some distribution, but the distribution is more like a single assignment, or we can think of it as at least a single assignment. And what we would like to say is that maybe based on different conditioning, so you chose a different set S and chose a different conditioning for that set S, maybe that recovered a different good assignment and hence possibly a different code word. So you want to just say that as you go over all conditionings, you probably recover the entire list. Of course, as stated, it's not true because the SDP solution could be a single assignment and you keep conditioning it, you'll never get anything. So what we do is essentially solve the SDP with an extra entropy term, or add a term which forces it to kind of in some sense incorporate any good code word or any good assignment. So we add some sort of entropic proxy to the SDP, and then a similar idea was also used in some machine learning applications by Raghavendra and Yao, and by Karmalkar, Clivans and Kothari. So for much nicer applications than the other KKK, but yeah, it's okay, and the idea is roughly. I mean, so let me just state what that proxy kind of is, and so we have these sort of local distributions which kind of are consistent on intersections, etc. I can use these to define also local distributions on. So this is the local distribution on bits of z, and I can use it to define local distributions on bits of y, which are the kind of output of the code word. So I can define let's say of size t over k. So then each of these bits only depends on k bits here. So I can use these local distributions to define ones here. And in particular, we kind of add a term which is where this is over the distributions for y, e, e prime. Okay. So this is something which depends on the SDP solution, but
How is the distribution on YT?
sorry. So yt is a collection of bits. Okay. I look at all the relevant bits in terms of z, sample a random assignment for the relevant z bits, and that gives me an assignment for the y bits. Okay. So it's just a local function. So as long as you have any local function, you can define this local ensemble. And this term you can show is a convex function of the SDP solution. So this is really what the part that actually defines the SDP solution. And like all convex functions, it sort of has this property that if you have some SDP solution such that the resulting code word in the Y space is in some sense very far from the SDP solution, then you can mix the two solutions. You can think of an integer solution just coming from a code word and the SDP solution and take a convex combination which will decrease this quantity. So you minimize psi. And the SDP, instead of a maximization problem, you write it as a constraint that the SDP value is at least something, which is the radius at which you are decoding. And you add a constraint, add a minimization condition on psi. And then you can show that the SDP solution which minimizes or is close to minimizing this has in some way at least some overlap with each of the kind of possible code words in the list for this Y space. Okay. So as you take this SDP solution and run the Barak-Raghavendra-Stoyer argument that you condition on subsets, you can recover something close to each of the code words in the Y space, which is the lifted code C, and then you again use some sort of unique decoding argument to get the relevant Z once you have the Y.
Distribution will support one.
It might. I mean, your list might have size 1, in which case it will.
Yeah,
Right. Sorry. Right. So. Right. So. Because phi is the convex function of the SDP solution. Which means that if you have yeah, so if you have two solutions which are very different, a convex combination will do better. I mean, you need to quantify all that, but the argument is just convexity.
It's partly motivated by some potential function you use in the conditioning to prove such a set exists or something? Or?
Not well. It's really just kind of the Frobenius norm of the SDP matrix. Once you are thinking of the moment matrix for the Y's rather than the Z's, so in some sense it's just a proxy for the rank of that matrix. We just wanted the matrix to be a high rank, and so Frobenius norm. Yeah, but that's about it. Yeah, I mean, we just wanted some convex proxy, which kind of led to lower rank.
And then what happens in the rounding phase once you have this?
So the rounding algorithm is the same. So you pick a random set, or in fact, you go over all sets S, you go over all assignments, and for each of them, you decode. What you need to prove is that for every true code word in the list, there is some rounding which recovers a code word close to that, and then such that you can go back by unique decoding. And yeah, that you prove using convexity.
So you're hoping that by fixing the conditioning step is with the disambiguation within the list.
Yes.
So after
Yeah.
having fixed
Precisely.
Yeah, but
There's
this
only
is,
one
all listed code.
Correct.
Algorithms are like that.
Yeah.
So, but this analysis is going to hope that at the end there's not going to be a mixture of other things. This convex thing will actually be a pure code word at the end. That's what you're hoping.
Well, so that we kind of get from here, that after conditioning we do get something pure. Right? This argument already shows you that after conditioning you get something close to an assignment or something pure in some sense, right? Because of this L1 distance condition, right? So what this is saying is that the kind of pure assignments that you get cover the list. And the covering the list part is because of the entropy. That we don't miss out something in the list. And that could have happened naively with an SDP solution, of course. So, yeah, so the extra piece of the argument is just saying that this means that you cover the list. Okay. Other questions?